Welcome back to our transport layer, and today I will start talking about the TCP. We're going to have two parts of TCP, but both of them are quite complex. So today I'll go in details of the TCP protocol, specifically what is the header, how we deal with the connection management, and how we do the basics of the flow control, like how this window management approach. So first of all, TCP. As I already showed this slide in one of the previous parts, TCP is a guaranteed service, so it provides the reliable in-order stream of data. It provides the management of the connection, so it has the capability to establish connection and tear down the connection, meaning that it will have the initialization of the state that I mentioned before, some form of initial sequence number in one direction, initial sequence number in the other direction. And as well, it provides these additional services like a full duplex, meaning there are like a connection kind of sequence number or reliability data transfer in one direction and reliability of data transfer in the other direction. We have a concept of the flow control, meaning we have this reliable delivery. And we have a concept of the congestion control, meaning TCP estimates how much traffic it can push to the network without causing overall congestion in the network. And to give you some ideas of what exactly is happening with the TCP header, I already highlighted that it's not that trivial. TCP header has tons of different fields. The first one, like source port and destination port, the one that uses for multiplexing and demultiplexing purposes. The sequence number and acknowledgement number these are accounting numbers that I've talked very similar to the ones I was talking in go back and selective repeat in the previous part, with one exception. In TCP, they don't count packets, but rather they count the bytes of the stream. So simply, if you send in kind of two bytes in your TCP stream, then they will be counted as a sequence number +1 and sequence number +2. The reason I kind of use the word sequence number instead of saying just 1 and 2, because the sequence number, initial sequence number, doesn't have to be 1, 0, or anything else. So this sequence number is actually, for security purposes, is randomized. Like every time you set up connection, you have like some random initial sequence number. Second one, there is also special receiver window. So this one I highlighted at the end of the previous part, which means that this amount of bytes a receiver is willing to accept at any given point of time. And even if your kind of sender's congestion control and other types of windows allow to send more, the receiver is asking sender to slow down. The other important fields that you will kind of have to know about is a few flags. So one flag is A, which means the acknowledgement, and if flag is set, like meaning if it's set to 1, then the acknowledgement number field makes sense. If flag is not set, then the acknowledgement number kind of field has to be present as part of the header. So that's kind of because its header is fixed. But the value of that number has no meaning to the receiver or to the recipient, which have to be the sender in one of our perspectives. Then there are two more fields, actually 3, but I'll focus on 2 of them, is SYN and FIN. So the SYN field or SYN flag, actually meaning synchronization, is really kind of to indicate that this is the packet is initiating the connection, or like initiating the sequence number, like the value of the sequence number. And I'll try to highlight it with a few diagrams on the next slides. And FIN or final, this is actually for the purpose of tear down. So basically, one flag indicated that the stream of bytes started, and the last one, the FIN, is indicating that the stream of byte ended. So basically, between these two flags, there's a flow of whatever packets that being sent out by the sender to the receiver, and this have to happen in both ways, as I will show you on the next slide. There's a few other flags like RST is a reset push, kind of to urgently push data to the sender. They're not really used too much. And one thing that I want to highlight here, is this the header length field. If you pay attention for the UDP packet header, there was a slightly different meaning of that. There was also a header. There was also length field in the UDP header, but it represented not the size of the header, but rather the size of the payload. And it was like 16 bits, like if you remember correctly. And for you question, and you definitely need to look it up RFC a little bit about to answer this question, is in this case header length is represented by, if I'm not mistaken, 4 bits. So maximum size of 16 effectively. But if you calculate whatever number of fields, it should be more than 16 bytes. And the question to you, generally, is how exactly it can happen. Like there is value from 0 to 16, and yet it's representing the header size that is definitely more than 16. And there can be actually much more than that. So please answer some of my questions. And as I said, you will need to take a very quick look into the TCP's RFC. To give you additional idea of what kind of extensions of TCP header can be, so there is this options field that can be additionally included, and there's a tons of different options that exist. And I think the most useful among all of this is timestamp. So with timestamp, you can kind of help a little bit more with calculating of retransmission timeouts. But for the purpose of lectures, for the purpose of our project too, we're not going to be using this one. Okay, so now really pay attention here, because this is really important, and I will be asking a bunch of questions about this one definitely during the exam. So management of sequence numbers and acknowledgement numbers. So what is happening with TCP is that the sequence number that is included, and the sequence numbers always have to be included as part of the packet, and it always makes sense, is this first byte in a segment of data. Look, if you already assume the connection is set up, and if you have a, if the sender has some data to send out, the sequence number will represent the next byte that will send out as part of this data stream. So effectively, if you have a payload, and this payload represents bytes 3, 4, and 5 of the stream that started with some other sequence number. So then the sequence number included in the header will be 3. So that's the basic idea. So the acknowledgement is actually a slightly different one. So the acknowledgement is if you receive the packet, like a TCP packet that had the 3, 4, and 5 sequence numbers, so the receiver knows that it's received, and as part of the acknowledgement number, it will include 345, that was 345 was acknowledged, and it will include 6 as an indication that it's expecting the next byte in the next sequence number byte to be 6. So the 6 has not been sent out by anybody, but this is the simply meaning that everything until but not including 6 has been received. This is the basic logic. And as I put in a question of how exactly to handle out of order segments if we receive something. So this one is not actually up to the standard of TCP, but rather the implementation both receiver and the sender side, and there were tons of various mechanisms that has been implemented over the years. Now another important part, connection setup and then connection teardown. So everything again is using this concept of sequence numbers and acknowledgement numbers as I talked before, with the exception that with the sequence number, with the connection setup, we didn't have yet the sequence number base setup. And in order to set up this base, we have to use the so-called SYN flag. And the key part is whenever SYN flag is indicated, then the sequence number indicated as part of the header that you're sending out is actually the base sequence number that will be used to kind of to initialize. And to avoid any problems, avoid any kind of ambiguity in the understanding of what was sequence number, what was not sequence number, you can assume that this SYN byte, like this, is actually carrying the imaginary byte. So I'll try to show an example what I mean by this imaginary byte. Simply, with SYN you indicate some number, which kind of kind of from the perspective of TCP stream, supposed to indicate the first byte of data that you're sending out. But you cannot include any data because it will be effectively discarded anyways. But then when you do acknowledgement, you acknowledge reception of this packet. Acknowledge reception of this imaginary byte, and you expecting the next byte to arrive is +1 on top of what you just received. And again, it will be much clearer on the next slide. And what I want to highlight in addition to this one is the three-way handshake process. So the process not just starts with you synchronizing with somebody else. It's a kind of you synchronize with the receiver, with the server in this case. And the server, as soon as as soon as you received your SYN request, effectively request for the connection setup, it tries to synchronize with you with its own sequence number. So these are two different sequences of sequence numbers. It's a little bit complicated phrase, but literally there are two differences of sequence numbers to initialize one-way reliable stream in one direction and second one-way connection in the other direction. To finalize everything what is happening in the picture, so you, as a kind of initiator of the connection, you send SYN. As a recipient of that SYN, you send SYN ACK. So you effectively SYN to establish your sequence number, and ACK to kind of confirm that you received the SYN from the receiver, from the original sender. You can actually send up separate packets, like one SYN, one ACK, but usually they're being combined. And finally, to confirm that the connection has been established on both sides, then you have to send acknowledgement to acknowledge that you actually received that SYN packet. As you also notice, the connection from the perspective of client and server is established at different points of time. So from the perspective of client, full connection is set up as soon as it received the SYN ACK message. However, from the server perspective, it's been established only half round trip later. And depending on what packets has been lost in this picture, then the time can actually increase. And to highlight what happens with the sequence numbers is exactly on this picture. So if I want to have a kind of establish the connection, so in kind of I randomly pick the value of my sequence, kind of my base sequence numbers to be 10,001. So I have to include the SYN flag in here and the sequence number. Whatever I specified for the acknowledgement is actually not used, and other parameters really depends on kind of other environmental parameters. Then, as a recipient of this SYN message, I'm acknowledging reception of this fake byte of 10,001 and saying that I'm expecting to receive 10,002 as the next sequence number. So this is kind of what I meant by the imaginary byte. In addition to that, I'm actually including my own sequence number, and again, in this time, I generated 300,010 as my base sequence number, which being sent out as part of the sequence number field in a packet. And on the other side, I'm again sending the sequence number 10,002 as indication that the first byte in my payload would be this one. You have to include this one even though your payload may be absolutely 0. So that could be the whole amount of data that you're sending. In this case, you simply just saying, I don't have any data, but the sequence number that I will be sending of data, if I ever send the data again, will be this specific, the byte with this sequence number. And if I'm including acknowledgement number, I'm acknowledging reception everything up to 310 and expecting the next sequence number in your data to be 311. So that's kind of the basic idea. To close the connection, at least one side have to call this close API, BSD API, which results in creating a FIN message sent out to the other side. And as a response to normal data stream, you have the server will have to respond with acknowledgement. If the other side have nothing to send more, then it can actually send the FIN immediately, and sometimes you can actually combine FIN and ACK. So you acknowledgement something, and you indicated that this is the last byte of the connection that you will be sending out. and kind of as a recipient, you will send ACK back. So the problem, kind of why I mentioned that this is actually incomplete picture, is a little bit of uncertainty. And this uncertainty means kind of about when the connection should be actually closed. So from the perspective of B, this is actually quite simple. So, and B is with respect to who exactly called the close first. So from B, you received FIN, you respond with ACK, you send FIN, you received ACK, and everything is fine. So you know that the other side closed the connection, and you kind of received the acknowledgement of your connection closing. So everything is fine. From the perspective of A, picture is quite different. You're not 100% sure that the connection on B has been finished yet. And the reason you're not 100% sure that, so what you're sure about is that you close the connection, like you have no data to send, and the other side acknowledging this part. And you know that B initiated the connection closing. But what you did not know that the B has actually received your acknowledgement, because the acknowledgement can be lost. And there is no acknowledgement for the acknowledgement, because otherwise still have to be like acknowledgement for the acknowledgement for the acknowledgement for the acknowledgement, and you can continue that forever. So what exactly should happen? And what should happen and what exactly is happening as part of a TCP protocol has some kind of a timed wait. And this timed wait means that the connection is kind of closed and kind of not closed. And if you remember, maybe some of you experienced the problem of, oh, I cannot, we're trying to rerun my server, and server is complaining, saying, oh, the connection is still, there is some server listening on the port. And it was because of that specific timed wait timer. And this timed wait timer can be reasonably large. So it's defined as a 2 MSL, and if you would like to confirm in RFC what exactly this MSL size is, but it's potentially can be significant. And it simply means to ensure that if the other side needs to retransmit FIN, you will properly reply with acknowledgement. And everything will be closed properly, and every kind of all connection will be closed down. To give you a very simple picture of TCP state diagram, so this one is actually a copy from RFC specification of TCP, and as you can see, it's not that simple. It has like 1, 2, 3, 4, like more than 10 different states with various different transition between them. There's a fin wait 1, fin wait 2, there's like time wait, closing, closed. So most of the complexity is related to establishment of the connection and the tearing down the connection. As soon as the kind of connection is established, then everything is fine. It's just everything being flown. There's you receiving data, you send in acknowledgement, like you're receiving data, send in acknowledgement. But as soon as you try to close the connection or establish new connection, there's a quite amount of uncertainty happening in between. I already highlighted in the previous model that you can check the state of the kernel about about like a demultiplex table for TCP and UDP. And as you can see, for TCP, you can actually get all these different states. So you can have some sockets can be in listen state, some sockets, TCP socket can be in like SYN-sent, meaning like you try to establish the connection, but you didn't yet get the confirmation from the other side that everything is fine. Some of them can be kind of with established connection, some of them close wait, meaning that you already established, you close the connection, and now you're waiting for the kind of for this 2 MSL to expire and effectively to remove from the state. I would advise you to explore UNStat, and as I highlighted, I think in playposit, that this command is for macOS, and for the Linux it's slightly different, but kind of essentially very, very similar. So in this example, what exactly happens is the connection being set up from the consumer, or from the client. Then the server accepts the connection and is trying to establish its own connection, like own the set of sequence numbers by yet another SYN flag. Then the client kind of acknowledges that it's received the SYN message from the server, and at this point, the client actually is able to start sending data. So what it's sending is the sequence number 35, meaning the first byte in the stream, in the payload of the packet that the sender is sending is the sequence number 35. If there's a data, then it will be the actual data being sent out. If there's no data, then you just simply act as an acknowledgement packet. If a server receives the packet and interprets it as a proper request, it starts sending, kind of look up for what to reply and start sending data back. As I said, really depends on how much MTU size is, or like how server is willing to send packets, or in how many chunks it wants to chop them. So it can do different ways. In the simplest case, it can send 100 bytes of data, meaning that it has acknowledgement to acknowledge the previous reception of the data. It has its own sequence number indicating that the first byte in the data that is sending out is 94 and sending the whole 100 bytes of data. And then it is a second packet that can send kind of with empty payload the packet that acknowledging, again, for some reason, acknowledging the sequence number 55. Have the fin flag, and the sequence number is 194, meaning the first packet in the payload, even though like payload in this case is 0, would be 194. One note here, to the second packet doesn't really have to have this acknowledgement flag. It may or may not be included. So this really depends on the implementation side. So it could have been just F and the sequence number. In addition thing, I could also show you the picture that the server sent out only one packet, which had the A, ACK, F sequence number data. So this would have been as acting as acknowledgement of previous data, sending actual data, and finishing up the connection, or like initiating the finishing up the connection. So that's a valid state. Another valid state if it was acknowledgement, ACK for 55, sequence number of 94, and 1 byte of data. Then the second packet is may or may not include the acknowledgement, but sequence number of 90, if I calculate correctly, 95, yet another byte of data. And like 100 packets of very similar to that one. And then acknowledgement at the end. So all of these options is exactly correct. It just really depends on specific environment, what exactly is happening on the server side, what exactly happened on the client side. It's really unknown at this point of time. And both server and the client have to be ready to accept all those information properly. So that's why kind of one of the tests that I did with the autograder was to ensure that you don't have any assumption about how many data you're receiving upon each receive call, or how much data you're sending out upon each send call. And I think that's it. So when the client receives the connection, it receives the fin flag, it knows that the connection is ended. And from 1.0 HTTP 1.0 logic, it indicates that the end of data that's been requested, and then it's just simply closing that connection and waiting for the acknowledgement. So there is somewhere at some point someone have to have this 2MSL, and in this case it's a server's responsibility to have this 2MSL timeout wait. And from the client perspective, it doesn't need to wait anything because the connection in closing was initiated by the server. If it was initiated on the other side, then it would be client's responsibility to keep the state. And just to summarize, so TCP is kind of very complex protocol, and it has all these sequence numbers, acknowledgement numbers. The most important part is this connection management, like connection set up in two directions. There is a connection teardown, and remember there is this complex process to resolve ambiguity of connection closing on both sides. Flow control is working in both directions, kind of individually in both directions, using the sequence number and acknowledgements. Acknowledgement flag is used to indicate whether this acknowledgement field makes sense or doesn't make sense. If it doesn't make sense, the number has to be present as part of the header, but it makes kind of no value, like the value has to be ignored. For the error detection, TCP uses two mechanisms. One of them is slow, this retransmission timer, and the other one is faster but less precise. And for the kind of this less precise is fast recovery and detection using usually 3 duplicate acknowledgement. This number can actually be adjusted, like on Linux specifically, but usually nobody actually bothers to touch this value. There's a concept of receiver window, or receiver flow window, just to restrict from the receiver perspective how much it's willing to accept. And there is a congestion control window that I'll talk about next time, simply to control this is from the network to control how much data needs to be sent out. And unfortunately, the network cannot really tell us how much it's willing to accept. So it's a sender's, in TCP, it's a sender's responsibility to estimate how much network is willing to accept. And we'll talk more about this next time. Okay, now definitely that's it for today. And again, hope it was interesting.